Hello, welcome to Winter Rosa Apiaries.
Are some cool cognitive skills of honeybees and a couple of friends. Just by the way science is done, a couple of the experiments I'm going to tell you about were done in things like bumblebees, but the principles still apply to humans. So, starting off with how smart are bees, we kind of need to think about what intelligence actually is. So when we think about what intelligence is, a lot of ideas might pop into your head. Things like IQ tests, or this kind of slightly horrifying and completely untrue diagram that suggests that your brain shrinks if your IQ is smaller. This is not true. Don't believe things like this. You might think of big, complex, naughty ideas. You might think of artificial intelligence with computers, or things like brain training apps that promise to help work out your brain. And intelligence is actually really hard to describe and to kind of put into words. There are some really weird ways that we've tried to define intelligence in the past. Like this person, Alexander Wisner-Gross, who tried to put an equation on intelligence. This will not be on the exam, don't worry. But the way he verbally described his equation was that intelligence is a force that acts so as to maximize future freedom of action. Intelligence doesn't like to get trapped. So this kind of suggests that intelligence has something to do with flexibility, with being able to overcome problems, but it's also, again, not very intuitive. We can't really get a lot out of this. This isn't something we can empirically test. And it's also a little bit anthropomorphic. It's kind of making intelligence its own separate force, when intelligence is really a characteristic of any particular individual you're talking about. So, a slightly better definition, this is very long, but I'm going to go ahead and read it out to you, is that intelligence is a very general mental capability that, among other things, involves the ability to reason, plan, solve problems, think abstractly, comprehend complex ideas, learn quickly, and learn from experience. It is not merely book learning, a narrow academic skill, or test-taking smarts. Rather, it reflects a broader and deeper capability for comprehending our surroundings, catching on, making sense of things, or figuring out what to do. So once again, we see kind of some themes here. That intelligence involves flexibility, being able to learn, being able to solve problems, to plan for the future, think abstractly. But this is still not really something we can test. This is sort of end goal oriented. It's about the characteristic rather than something you can actually measure. But all of that being said, that's kind of an idea of what intelligence is. So the question at hand, how intelligent are bees? Or based on our definition, do bees have the ability to reason, plan, solve problems, think abstractly, comprehend complex ideas, learn quickly, or learn from experience? So when we think about bees compared to other animals, we used to think that insects were just reactive machines. You put in a stimulus, you get out of behavior. You put in a stimulus, you get out of behavior. We thought that all behaviors were hardwired, that everything was based on innate instinct, and that nothing was learned. As it turns out, this is true in some cases, but not all. This could be better written that insects can be reactive machines, where you put in a stimulus and get out of behavior. Some behaviors are hardwired, and some behaviors are based on innate instinct, but many more are actually learned. Many more behaviors that bees exhibit, and other insects, are complex, are capable of change. So we need a better definition in order to actually be able to do these experiments. So we have this operational term called cognition. Cognition is the process of acquiring knowledge and understanding through thought, experience, and the senses. So whereas intelligence is kind of an end goal, it's sort of the actual property of an individual, cognition is the process of gaining this knowledge and understanding. And cognition, clicked on something, that's exciting. There we go. The next screen press will be a right click. interesting. I don't know what I did there. Sorry about that. Anyway, whereas intelligence is an end goal, cognition is a process, and something that we can directly test and measure. So when we're looking at where bees sit on the cognitive scale, we tend to like to order things as humans. We like to say, this is the smartest animal, this is the next smartest. You've probably seen diagrams like this. It's really tiny, but it has gradings. At the top is the smartest animals. Below them, New World monkeys, then whales and dolphins, dogs, octopi, going down from there to animals that are considered less intelligent. And this is not a new idea. This is something that's been around for a long time. This is actually a print from the medieval era called the Great Chain of Being. The Great Chain of Being was the idea that you have God at the top, angels and demons below them, then humans, then wild animals, domesticated animals inherently below wild animals, going down to things like plants, then earthworms, fungus, things like that. And this is how humans intuitively like to think about things, but of course, nature isn't that simple. You can't put things on a timeline and say, this is the smartest, this is the dumbest. So instead of thinking about things like that, scientists tend to just look at some key, what are called cognitive skills, to get an idea of how intelligent an animal is. And some of the key cognitive skills that we look at are things like language. So in this picture, you have Coco the gorilla, who was actually taught hundreds of signs in American Sign Language and was able to communicate with her keeper that way. So being able to use language is a very impressive cognitive skill. Here you see a chimpanzee doing what's called the mirror test to show that this chimpanzee has what's called self-awareness, knowing that that image in the mirror that's doing the same thing that you're doing is actually you and is not some other organism. Here we also have tool use as a cognitive skill that scientists like to measure. Here we have a crow who has fashioned a little hook out of a piece of metal so that she can get a food reward that's at the bottom of this tube that she normally couldn't reach. Categorization is another cognitive skill that scientists like to look at. What is going on? Categorization is another cognitive skill that scientists like to look at, which is basically being able to pick out important traits that are similar between a group of items, and then using those traits to categorize new pieces of information. So for instance, maybe the pigeon is shown a red triangle, a red circle, a red diamond, and those are all rewarding. Then the pigeon is given something like a red hexagon. It's never seen a hexagon, but it knows that the color red has been rewarding in the past, so it can put that red hexagon into that category. And being able to do that is a cognitive skill that we look for. Finally, numeracy. Being able to count, to be able to understand different quantities, be able to compare quantities. Here's a picture of a black bear and a computer, because black bears are actually able to count a little bit and to handle numbers. And the original experiment that figured that out had black bears in front of a touch screen and was having them tap things on the screen. I couldn't find a picture from that actual study, so instead here's a picture of a bear who broke into someone's office and is putzing around on their desk. So, these are all things that we tend to look for when we're looking for signs of animal intelligence. Where do bees stack up? How many of these do bees exhibit? Despite the fact that they're teeny tiny, and they have teeny tiny little brains, bees actually exhibit a lot of these really complex cognitive skills. Bees have use of language, they've been shown making and using tools, they're able to categorize, and bees actually have a very impressive handle of numeracy, even more so than a lot of vertebrates, which we'll get into a little bit later. So clearly, bees are indeed intelligent. Part of the reason that this makes sense is that bees, in their natural day-to-day lives, face a lot of cognitive challenges that they need impressive cognitive skills to overcome. So just a small selection of cognitive challenges that bees face every day. They have to be able to do what's called associative learning, which is basically learning to forming an association between a particular stimulus and a reward. So say this bee is flying around in this field of white and yellow flowers that it's used to, and it comes across a pink flower. And that pink flower has a really great nectar reward. That bee needs to be able to make an association between the color pink and a reward, so that in the future, if it comes across another pink flower, it it knows, hey, that's a good thing. I should go there and check that out. On the other hand, on the other side of things besides associative learning, bees also need to have what's called extinction learning, which is the exact opposite process. It's basically unlearning things. So if you think about that, this bee's been flying around, it's learned that the pink flower was rewarding, great. After a few weeks though, that flower is probably going to stop producing nectar. Flowers don't produce infinite nectar forever. And so once the pink flowers have stopped being rewarding, that bee needs to unlearn that association, because otherwise it'll waste a bunch of time visiting pink flowers that are no longer any good for it. It needs to be able to use extinction learning to unlearn that association and not waste its time. Another cognitive challenge that foraging bees face is something called central place foraging. So, as we all know, bees have a central hive that they have to go to and from, and they have to be able to navigate around a really complex environment and make it back home. This is in contrast to other pollinators, something like a butterfly, that can kind of just live wherever it lands. That butterfly can flit around between flowers, drink nectar here, drink nectar there, go to sleep on whatever flower it lands on. It doesn't really truly need to be able to navigate. Bees do, and they are very, very good at it. Finally, another cognitive challenge that bees face every day is they have to be able to learn how to access many unique flower shapes. So you see all these weird-looking flowers in nature, and bees have to be able to learn how to manipulate any given number of flowers so that they can access the resources inside. And being able to learn this for different flowers requires completely different motor skills, completely different cognitive skills to do that. So they're able to learn all of these things. So, what have scientists done to actually test bee cognition? This is a small selection of some of my favorite experiments. First up, starting simple, we have Pavlov's bee. You've probably heard of Pavlov's dog. Pavlov was a scientist who would feed his dog meat. Whenever the dog saw the meat, he would start to drool because the meat smells so good and the dog's getting ready for a tasty meal. What Pavlov started doing is he would ring a bell right before he would give the dog its dinner. So ring the bell, give him the dinner. Ring the bell, give him the dinner. Pretty soon, that dog forms an association between the bell ringing and getting fed. So after a while, you don't even have to have the meat there. If Pavlov rings his bell, his dog's going to start drooling even with no meat there. Bees do the same thing, except instead of drooling, they use what's called the Proboscis Extinction Reflex, or PER. PER is basically stick out your tongue for sugar. And we use this to test their ability to learn associatively, to make an association between a new odor and a reward. So here's how it works. You have a little tube that pops in an odor, something like peppermint. It has a distinctive smell, but doesn't inherently tell the bee this is food. You give them a smell like peppermint oil, and then you give them a little bit of sugar water on the end of a stick. And that bee, when she tastes the sugar water with her antenna, will stick out her tongue. You keep doing this over and over again, and pretty soon, you don't need to have the sugar anymore. If you give her that peppermint smell, she'll stick out her tongue. So when we test bees on a very simple PER experiment like this, you find that bees do actually learn, and they learn really fast. Within 3 trials, the bees were able to consistently stick out their tongue for the odor after just 3 times of being given odor and sugar. So something that's a little, irksome about this when you're looking at that graph is it kind of seems like the curve is leveling off at about 80%. Why is that? Why is it that the bees stop getting better around 80%? There are 2 big reasons. First off, it's not as easy as it looks. When we're doing experiments with humans, we can explain to them what they're supposed to do. We can tell them what they're supposed to pay attention to, and a lot of things are familiar to them. Like, if you're doing an experiment and a scientist walks you into a room, you know that you probably don't need to worry about things like the color of the walls or the fact that there's a table in the room. But a bee, when we stick them in these paradigms, everything is new to them. Being in that little harness is new. There's all sorts of weird smells, weird lights, weird colors, and they don't necessarily know what the important information is, so we can't tell them. Additionally, and I think more importantly, bees live out in nature and nothing in nature is permanent. When we're doing these experiments, we make hard and fast rules, like when you smell peppermint, you're going to get a reward. But as we talked about earlier with Extinction Learning, this is not the case in nature. And in nature, it pays to sometimes try the wrong choice to see if it's become the right choice since last time you checked. So if you ever see these curves leveling off at 75, 80%, it doesn't mean anything necessarily about the bee's ability to learn. It actually says something about their flexibility. It is a good thing, not a bad thing. Okay, next cool cognitive things. Honeybee math, or bees can understand abstract concepts. So first off, this experiment showed that honeybees are capable of counting. This is what was called a delayed match to sample Y maze. This is a top-down view. So the bee starts at the base of the maze, and there she's given a little sample card that has a certain number of shapes on it, like 3 triangles, 5 diamonds, something like that. After she sees the sample card at the entrance, she has to walk down the base of the Y, and she comes to the fork. At the fork, she's given 2 choice cards, one of which matches the sample, and one of which is different from the sample. She has to remember how many shapes she counted on this card, find the card that has that same number of shapes, and choose that side. If she chooses the correct side, she gets a reward. If she chooses the wrong side, she just finds an empty room. So this is kind of what it would look like from the perspective of a bee. You start at the base, you see the card, you see how many shapes are on the card, you walk down, and you have a choice. We have 2 here, 3 here. So, quick test of your ability to count. Which direction should she go, left or right?
Right.
Right, exactly. If she goes right, she gets sugar. If she goes left, she gets nothing. One important thing I want to point out. This is not something where the bees are just learning to remember a picture. Because if you remember exactly what the original card looked like, it did have 3 stars. But they were in a different position and a different orientation. So the bee isn't just remembering a snapshot of what a picture looked like. She actually has to count how many shapes there are on each card. And bees, this experiment showed that they're actually very good at counting, up to about 5 or 6. So if we look at these graphs, when the sample pattern was 3, she more often chose the choice card with 3. When the sample card showed 2, she more often chose the card with 2. And this was the case even when they changed what the pictures looked like. So even when they were given a sample card with 3 blue circles, they were able to consistently pick the card with 3 yellow stars. So they weren't even matching the images, they were actually counting the number of unique elements. So this goes to show honeybees can count. Cool, good for them, they can count to 6. Even cooler than that though, honeybees can actually perform math problems. Very simple math problems, to be fair, but they can perform math. They used the same delayed match to sample Y maze, but instead of learning to match the sample, they taught the bees to either add 1 or subtract 1 from the sample number. And they did that based on the color of the card. If they were shown a yellow card at the beginning, that means subtract 1. So say you're shown 3 yellow squares at the beginning, the bee knows yellow, I need to subtract, 3 minus 1 is 2, I need to pick the sample with 2 shapes on it. Blue meant they needed to add 1, so for instance, if you start with 2 blue squares at the beginning, blue means add 1, 2 plus 1 is 3, the bee needs to pick the card with 3 elements on it. And I will not go into the full details of all of the different combinations they tried, but I do want to stress that they made sure to use combinations that checked to make sure the bees weren't just doing something like anti-matching. They didn't just pick the one that didn't look like the card they had already seen. For instance, with this blue card, she has 2 here, and she has the choice between 1 and 3. So it's not like she could just say, I need to pick the one that's not 2. She did actually have to know that she needed to add 1 to get to the side of 3. And what you can see with this curve shows how well they were able to learn. And once again, after many, many trials, they were able to learn to do this. They were able to learn to add and subtract from their sample card. One thing I want to point out, this took a lot longer than just learning like the PER paradigm or just learning how to count. If you can see on the x-axis here, the number of trials, they really started to level off once they got to more like 90 or 100 practice trials. Because once again, nobody told the bees, here, do math, add 1. The bees just had to, by trial and error, figure out what the pattern was. And also, I would like to point out once again, this curve is starting to level off around that 80% mark again. Like we talked about earlier, shows that these bees are remaining flexible. Okay, so up next, this experiment was done with bumblebees. There's actually a lab in France that does a lot of work on bee cognition. They choose to use bumblebees instead of honeybees, but a lot of these principles still apply. So, this is bumblebee cognitive flexibility, which is the ability of bumblebees to solve complex problems. So, when scientists wanted to test bees' ability to problem solve, they needed to give them a task that was completely unnatural. If they gave them some sort of task that they would find out in nature normally, then it could be that that task is based on instinct. No matter how complex it was, it could be completely instinctual. They had to give them something that there is no way they would ever have come across in nature for them to figure out how to do. So what they did was they trained them to roll a ball to access a reward. So you can see she starts out here with this little ball. This is a bee that's already been trained. She grabs it, she rolls it backwards, and when she gets it in the center, in that target, she gets a little bit of sugar water to reward her. And the bees were able to learn to do this really well, which again, obviously a completely unnatural behavior. You're not going to see a bee doing this out in the wild on a flower. Even with their teeny tiny little brains, not only were they able to solve this problem, they were actually able to improve on it. So one element of this experiment, they always trained the bees by having that ball in the same place. You can't tell it in this video, but when they were training the bees, they had little markers on the board to help the bee orient itself. And they always had the ball in this particular spot. So they were trained, this yellow ball in this spot, roll it here, get the sugar. What they did after the bees had been trained for a while, they introduced a second ball. It was black, so it was a different color, and it was about twice as close. They put it around here. But it was black, and it was in the wrong place. And so if this was the kind of fixed learning that the bees only were able to learn this, get this ball in this spot, move it here, then you would expect them to go and pick the yellow ball. But that's not what happened. These bees understood the behavior at a more complex level and were able to improve upon it by instead picking the closer ball that was a different color and using that to fulfill the task. Which suggests that they actually understood what the point was and they weren't just sort of repeating this behavior in a stereotyped way, just kind of doing what they've been programmed. And so this is a graph showing their learning. This is a little bit non-intuitive. Most of the graphs we've been looking at show the percentage correct, so you expect that to go up over time. Instead, this y-axis shows the solving time, basically how fast they were able to do it. So in this case, if they're learning well, you want to see it going down, because you expect them to be able to do it faster as they learn better. And that's exactly what we see. One thing to note, though, there is a lot of variation here. So you can see individuals like this one that's in blue triangles on the bottom was always pretty good at this. They started off being able to solve it quickly, and they only got better. You have some other individuals, like this individual with the red rectangles, that it took them a little longer to figure out how to do it, and they were able to improve on their time overall. This is important because not all bees are the same. Not all bees are going to be able to learn individual tasks as well. Some individuals are more innovative. Some of them are better at learning what they've already been, doing what they've already learned.
So why did that bee try to move the ball in the first place?
Really good question. I was going to show a longer video, but I do not have access to the internet, so I had to stick with this really short one. In the experiment, the first couple times they put the bee in the arena, they had a little fake bumblebee that was made of plastic. It was the same size as the bumblebee, and it had black and yellow stripes, and it was on a stick. And the scientists would use that fake bee to push the ball, and they would let the bee watch this sort of fake bee demonstrate how to do it. Now, because it was just a piece of plastic, it didn't show them kind of the motor pattern that they needed. It didn't show them how to grab the ball and actually roll it, but it showed them the idea that if this ball ends up here, you get sugar. So that's how they initially trained them. Really good question. So, I'm gonna get up on my soapbox for a little bit. As a scientist, I have to bring this up because this particular experiment came with all sorts of baggage with it. So I already told you why scientists did this experiment. They wanted to see, even with a teeny tiny little bee brain, can this bee solve a complex problem? Because that can help tell us something about what our giant brains can do in terms of problem solving, right? Well, when this experiment broke to the media, this is how it was portrayed in popular press articles. Scientists teach bees to play soccer. Watch them up their game. I understand why the popular press articles worded it this way. A cutesy title like that will get a lot of clicks onto your article. And that's what they're in the business of. They're in the business of getting people to interact with their article. But the problem is that when you word it in kind of a cutesy way, like teach bees to play soccer, it trivializes why the scientists did it, and it misleads people about the importance of the work. And so, on this particular article, if you scroll down onto the Facebook comments, which is never a good idea, but I did it and took some screenshots, this is the kind of things you'll see. So many things to help research in the world, and we have scientists doing this bull. WTF, nothing better to do in this world than harass bees. Things like, why is this even a thing? We know bees are smart, now find a cure for Alzheimer's without imprisoning anything. And the list goes on from there. People who are worried about the dollar amounts. I can only figure this wasted thousands of dollars, signifying little, but would have had a more significant impact by research and effort into preserving all bees' habitat and diminishing the pesticidal effects of this type of pseudoscience. For people who are worried about the cost, I can assure you this experiment did not cost thousands of dollars. This, first off, also was not even done in the US. A lot of the outrage came from the US. This was done in France. None of your tax dollars went to this experiment. Even if they did, it probably cost a couple $100s. So if it had been done in the US, you might have paid something like 1/10,000th of a penny to go towards this experiment. So people who have those kinds of concerns, I want to allay them right now. This doesn't cost that much to do these kinds of experiments. Second off, there was an important reason to do this. If the purpose had been just to create soccer-playing bees, if that had been the goal of the scientists, I would agree with the goal. Haha, pun. If that had been the goal, I would agree that this would have been a waste of time, a waste of resources. But that wasn't the point. So, I'm coming here humbly before you today, beseeching you, asking you, if you see a headline and your first thought is, why would anyone waste time and money doing that? Please ask yourself if it's an accurate representation of what scientists did and why they did it, or if it's a sensationalized headline. I can almost guarantee it's a sensationalized headline. So, getting off of my soapbox, back to cool things bees can do with their brains. This is actually not bees at all, this is wasps, but it's actually really cool, so I just wanted to talk about it for a minute or so. Everyone's least favorite garden friend, the paper wasp, actually is able to use facial recognition to tell individuals apart. So all of these different wasp faces are the same species. This diversity that you see is within one species. And this is how individual wasps tell each other apart. They have this system because wasps actually, unlike bees, have a very strict hierarchy within their nests. Instead of having like a queen and a bunch of workers, they have a very set sort of linear hierarchy amongst all of the individuals. And so being able to recognize faces is really important because they don't just need to tell a nestmate from a non-nestmate, they need to tell a superior from a subordinate. And they are very, very good at distinguishing faces. Even if you strip away most of the information and just give them the important lines, like here you got some little horizontal blips and some bigger horizontal blurs, they can even tell who's a nestmate, who's above them, who's below them, from little bits of stripped out information like that. So that's cool for paper wasps. Next time you're being harassed by them on your porch, something to think about, make you appreciate them a little more. Back to bees though. We talked at the beginning about how categorization is one of the cognitive skills that scientists really look for when they're trying to see how intelligent an animal is. And honeybees are really good at categorization. So what this experiment did was they showed them little triads of shapes. Within the three shapes, one of them would be symmetrical, two of them would be asymmetrical. And they would only reward the bees for visiting the symmetrical shape. So first they'd show them this one, they'd only reward the symmetrical one. They'd show them a completely different set of shapes, only reward them with the symmetrical one, on and on down the list. And so the bees were not really exactly being trained to learn that certain shapes were good. They had to learn the rule that in any given set of shapes, it's the symmetrical one that's rewarding. And then, for the test, after they'd been trained, they showed them a completely new set of shapes that they had never seen before, and measured how quickly they were able to learn to pick the symmetrical one. And once again, they were able to learn to do so very well. The cooler one in this categorization field, though, like, that's, scientifically rigorous, blah, blah, blah. It's boring, though. The fun one, scientists used this and showed that bees were able to categorize paintings by artist. So they showed that honeybees, if trained, can tell a Picasso apart from a Monet, even if it's never seen the painting before, if they've been trained well enough. So they would show them these pairs of paintings, one a Picasso, one a Monet. They would only reward them for going to the correct artist. And they trained them on both to make sure they could learn equally well either way. And once again, they would do that over and over again, give them a novel pair that they had never seen before, and test their ability to distinguish them, and they were able to. And something else that I'm not showing the data for because it gets really big and long and confusing, but they were trying to figure out what exactly it was that the bees were cueing into on these different paintings that was telling them which ones belonged to which artists. So they did things like they repeated the experiment in black and white. They were still able to tell them apart. They did things where they controlled for the amount of hard edges versus soft edges. They were still able to tell them apart. They did tons of image manipulations, and in all of the cases, the bees were still able to figure out which artist was the correct one. So what they believe this shows is that honeybees, kind of like when humans are looking at a painting, aren't cueing into any one detail. They're taking in the whole suite of visual information and processing that really complex mix of data and using that to help them figure out which artist or which category a new painting would fall into. So finally, my last favorite cognitive ability of bees, this is back to bumblebees, the same group that did the bumblebee soccer, showed that bumblebees can actually learn